Good day, stargazers, and welcome to Astronomy Daily, episode 41 of season 5. I'm Anna.
And I'm Avery. And what a day to be alive and looking up, Anna. It's Tuesday, February the 17th, 2026, and we have not one, but two celestial events happening today.
That's right. The sun is about to be turned into a ring of fire over Antarctica, and a comet that may never return is making its closest pass to Earth as we speak. Plus, we've got JWST solving an identity crisis for some massive exoplanets, NASA doing CT scans on the northern lights, and a startup that wants to fuel rockets with water. And a preview of why 2026 might just be the greatest year of eclipses in a generation.
Let's not waste a single second. Let's dive right in.
So, Avery, we've been building up to this for weeks, and today is finally the day. Right now, as many of our listeners are tuning in, an annular solar eclipse is tracing its path across Antarctica.
And I know some of our listeners might be thinking, didn't we just cover this? And yes, we've talked about it in recent episodes. But today is the day, and there's something truly special happening down at the bottom of the world.
Let's recap the essentials. An annular eclipse happens when the moon passes directly between the Earth and the sun. But because the moon is at a more distant point in its orbit, it doesn't completely cover the sun's disk. Instead, you get this breathtaking ring of brilliant sunlight surrounding the dark silhouette of the moon.
The Ring of Fire, and today's ring will last up to 2 minutes and 20 seconds for anyone lucky enough to be standing in the path of annularity. At the moment of greatest eclipse, which occurs at 12:12 UTC, the moon will cover approximately 96% of the sun's surface.
Now, 96% sounds like almost everything, but here's the important thing. It's not a total eclipse. The sky won't go dark. You absolutely must keep your solar eclipse glasses on for the entire event. There's no moment where it's safe to look at the sun with the naked eye.
The path of annularity itself is actually quite wide for eclipse standards, about 616 kilometers across. But it's crossing some of the most remote territory on Earth. We're talking about the Antarctic mainland and the surrounding Southern Ocean. So realistically, the only people seeing the full Ring of Fire today are researchers at a handful of Antarctic stations.
However, the partial phases of the eclipse are visible from a much wider area. Observers in southern Argentina, southern Chile, southeastern Africa, Madagascar, and Mauritius will all see the moon take a bite out of the sun to varying degrees.
And here's something that I think really elevates today's event. This eclipse kicks off the first eclipse season of 2026. Eclipse seasons are these brief windows, typically about 34 days long, when the geometry of the sun, earth, and moon aligns just right for eclipses to occur. And they usually come in pairs.
Exactly. So less than 2 weeks from now, on March the 3rd, we get a total lunar eclipse, a blood moon, visible from North America. And that's just the beginning for 2026, which we'll come back to later in the show.
For anyone wanting to follow along today, there are several live streams available, and we'll have links in our show notes. Even if you can't see it from where you are, this is a wonderful moment to appreciate the clockwork precision of our solar system.
And sticking with things happening literally today, let's talk about Comet C2024 E1, better known as Comet Wierzchoś, which is making its closest approach to Earth right now.
This is one of those stories where the science and the poetry really come together beautifully. This comet was discovered back in March 2024 by Polish astronomer Kasper Wierzchoś using the Mount Lemmon survey in Arizona. And today it passes within about 151 million kilometers from Earth, roughly the same distance as Earth is from the sun.
So it's not exactly a close shave, but it's still a significant astronomical moment. What makes this comet truly special is that it's on a hyperbolic orbit. For our listeners who aren't familiar with that term, it means the comet's trajectory isn't a closed loop. It's not coming back.
Ever. Or at least not for over 200,000 years, and even that's optimistic. Scientists believe it originated in the Oort cloud, that vast icy shell at the outer edges of our solar system. and it's now getting a gravitational slingshot that will send it out into interstellar space. This is genuinely a once-in-a-civilization event.
NASA's astronomy picture of the day featured Comet Wierzchoś today with a 30-minute exposure taken from Chile, showing a gorgeous 5-degree long ion tail and 3 separate dust tails. The comet also has a vivid green coma, which scientists believe is linked to carbon-bearing compounds, likely diatomic carbon, fluorescing under ultraviolet sunlight.
The James Webb Telescope actually observed this comet last year when it was still far out at about 7 astronomical units from the Sun. They found its activity is primarily driven by carbon dioxide rather than carbon monoxide, which is interesting because it suggests the comet may have lost its near-surface CO early in its evolution.
Now, in terms of actually seeing it, at magnitude 7.8 to 8.2, you're going to need binoculars at minimum, ideally a small telescope. It's currently in the constellation Sculptor, quite low in the southwestern sky after sunset. Southern Hemisphere observers have the far better view today.
Northern Hemisphere observers don't despair. Over the coming days, the comet will climb a bit higher, and by around February 23rd, it should be a more accessible target as it passes near some galaxies in Cetus. But it will be fading by then. If you can get out tonight with some optics, it's worth the effort. You're quite literally saying goodbye to something the human race will never see again.
All right, let's travel 133 light years away to the constellation Pegasus, where the James Webb Telescope has just settled one of exoplanet science's most persistent mysteries.
And the key to solving it? Hydrogen sulfide, the molecule that gives rotten eggs their delightful aroma. Published in Nature Astronomy, a team from UCLA and UC San Diego used JWST to study HR 8799 system, which hosts 4 enormous gas giant planets, each between 5 and 10 times the mass of Jupiter.
Now, these planets have been known since 2008, and they're actually directly visible through telescopes, which is remarkable in itself. Most exoplanets are detected indirectly, but because they're so massive and because they're so far from their star, between 15 and 70 times Earth's distance from the Sun, scientists have long debated if they're truly planets or something else entirely.
Specifically, are they planets or brown dwarfs? Brown dwarfs are sometimes called failed stars, objects that form through gravitational collapse of a gas cloud, like a star, but never got massive enough to sustain hydrogen fusion. The traditional mass boundary is around 13 Jupiter masses, but that's a bit arbitrary.
What really matters is how they formed. Did they form like planets through core accretion, building up a solid core from dust and rock that then attracted gas? Or did they form like stars through the rapid collapse of a dense pocket of gas?
And this is where the rotten eggs come in. The team detected hydrogen sulfide in the atmospheres of these 3 worlds, HR 8799c, D, and E. Now, why is sulfur the key? Because at the vast distances these planets orbit their star, sulfur can only exist in solid form within the protoplanetary disk. It cannot be in the gas phase. So if there's sulfur in these planets' atmospheres, it had to have been gobbled up as solid material during the planet's formation.
That's the smoking gun for core accretion. These worlds, massive as they are, formed the same way Jupiter did, just on a much grander scale. Previous studies looking at carbon and oxygen couldn't distinguish between the 2 formation pathways because those elements can come from either gas or solids.
The researchers also found that these planets are enriched in heavy elements compared to their host star by factors of roughly 2 to 9 times. They estimate the 4 planets together contain around 600 Earth masses of heavy material. That's an extraordinary amount of solid material.
And this raises a really fascinating question. How big can a planet get? If objects 10 times Jupiter's mass can form through core accretion, where exactly is the line between the biggest planets and the smallest brown dwarfs?
Lead researcher Jerry Swan from UCLA put it beautifully. He said the technique they use to separate the light from these incredibly faint planets, 10,000 times fainter than their star, will eventually be applicable to studying Earth-like worlds. He said finding an Earth analog is the holy grail, and we might be 20 to 30 years away from getting the first spectrum of an Earth-like planet and searching for biosignatures.
The future of exoplanet science built on the foundation of smelly gas. Who would have thought?
Staying closer to home now, well, relatively speaking, NASA launched 2 groundbreaking sounding rocket missions from Alaska earlier this month, and the results are already exciting the science community.
These launched from the Poker Flat Research Range near Fairbanks, and they had 2 of the best mission acronyms I've ever encountered. The first is BADASS, the Black and Diffuse Auroral Science Surveyor. And yes, that's the real name.
Launched February 9th, BADASS reached an altitude of about 360 kilometers and was specifically designed to study a phenomenon called black auroras. These are these strange dark structures that appear as gaps or voids drifting within the brighter diffuse aurora, like someone has taken an eraser to parts of the northern lights.
What's happening physically is that electrons, instead of streaming down into Earth's atmosphere the way they do in normal auroras, are shooting upward into space. Scientists don't fully understand why this reversal happens, and BADASS was designed to gather data on exactly that.
Then, on February 10th, NASA launched the GNEISS mission. That's the Geophysical Non-Equilibrium Ionosphere Science System. This one used 2 rockets launched just 30 seconds apart, flying side by side through the same aurora along different slices.
And here's the clever bit. Each rocket ejected 4 sub-payloads, giving them multiple measurement points inside the aurora simultaneously. The rockets also sent radio signals through the surrounding plasma to a network of 11 ground receivers. The way the plasma altered those radio waves allowed scientists to map the plasma density, revealing where electrical currents can flow.
Principal investigator Christina Lynch from Dartmouth College described it as essentially doing a CT scan of the plasma beneath the aurora. In the same way a medical CT scan uses X-rays passing through different body tissues to reconstruct the 3D image, NEISS uses radio waves passing through auroral plasma to reconstruct the electrical environment in 3 dimensions.
Both missions reported that all instruments performed as expected and returned high-quality data. This is particularly satisfying for the BADASS team because the same mission was on the launch pad at Poker Flat last year, but the required auroral conditions never materialized before the launch window closed.
Understanding how auroral currents work isn't just pure physics. Those currents shape how energy from space spreads through Earth's upper atmosphere. Where the current fans out, the atmosphere heats up, which can affect satellite drag, GPS accuracy, and radio communications. With our increasing dependence on space-based technology, this research has very practical implications.
Now, for something that sounds like science fiction but is heading for a real-world test later this year, a startup called Galactic, led by former SpaceX engineer Hallen Madison, is developing technology to use water as rocket fuel.
And before anyone thinks we're talking about some kind of perpetual motion scam, the science here is sound. The core concept uses electrolysis, splitting water molecules into hydrogen and oxygen, and then using those gases in 2 different propulsion systems.
Right. For chemical propulsion, you burn the hydrogen and oxygen together, which produces high-pressure thrust, much like a conventional rocket engine. For electrical propulsion, you ionize the oxygen and accelerate it using a magnetic field, creating plasma thrust. Madison describes that second type as very, very low thrust. People jokingly like to call it a burp in space.
But even a burp in space can be useful for precise maneuvers and station keeping. The real game changer here isn't the propulsion technology itself, but the fuel source. Water is one of the most abundant resources we found on other worlds. There's water ice on the moon, on Mars, on asteroids. If you can turn that water into fuel, you've essentially created the infrastructure for cosmic refueling stations.
That's exactly Madison's long-term vision. He's talking about building a refueling network that connects Earth, the Moon, and Mars. As he puts it, everybody wants to go build a moon base or a Mars base. Who's going to pay for it? How does it actually work? His answer is to make the economics viable by using in situ resources.
Now, there are real challenges to overcome. Water has to be purified, electrolyzed, and stored efficiently, and the whole system has to be lightweight enough for space applications. There's also concerns about ionized oxygen potentially affecting satellite electronics, but the team is pushing ahead with a proof of concept.
And that proof of concept is coming soon. General Galactic is planning to launch an 1,100-pound satellite on a SpaceX Falcon 9 rocket in October 2026. That satellite will test both the chemical and electrical propulsion systems using water as fuel in actual space conditions.
If it works, it could fundamentally change the economics of spaceflight. Matheson claims they're talking about billions of dollars in savings even with current operations, and trillions in new economic growth as the infrastructure scales up. Those are bold claims, but the underlying physics is solid. We'll be watching that October launch very closely.
So we open the show with today's annular eclipse, and we mentioned that it kicks off an eclipse season. But I think it's worth zooming out and looking at the bigger picture, because 2026 is shaping up to be an absolutely extraordinary year for eclipses.
It really is. So let's run through what's coming. First up, as we mentioned, on March the 3rd, we get a total lunar eclipse. That's a blood moon, and it will be visible across North America, which is fantastic news for our listeners in that part of the world.
Then we get to August 12th, and this is the big one. A total solar eclipse, not annular, but total, with its path of totality crossing the Arctic, Greenland, Iceland, and Spain. And observers across much of Western Europe and North America will see a partial eclipse.
For anyone in the UK, this is particularly exciting. The BBC Sky at Night magazine and the Royal Observatory Greenwich are both flagging this as the best solar eclipse visible from the UK since 1999. Viewers in London will see the moon touch the edge of the sun's disk at 6:17 p.m. BST.
And it doesn't stop there. The astronomical community is talking about a genuine golden age of eclipses beginning right now. Between 2026 and 2028, we're looking at 3 total solar eclipses and 3 ring of fire eclipses in just 3 years. That's an extraordinary run.
So if today's Antarctic Ring of Fire has you feeling a bit left out because you couldn't see it, don't worry, there is so much more to come. Start planning now for August 12th and make sure you're subscribed to Astronomy Daily because we'll be covering every single one of these events.
This is going to be an epic year for eclipse chasers.
And that brings us to the end of another packed edition of Astronomy Daily. What a day, Anna! An eclipse, a comet farewell, rotten eggs solving planetary mysteries, CT scans of auroras, water-powered rockets, and a golden age of eclipses beginning right now.
If you enjoyed today's episode, please do subscribe wherever you get your podcasts. Leave us a rating and a review, and share us with anyone you know who loves looking up. You can find us at astronomydaily.io, on YouTube, and across all social media platforms at Astro Daily Pod.
And don't forget, we're part of the Bytes.com podcast network, where you'll find plenty of other great shows to keep you entertained and informed.
Until next time, keep your eyes on the skies.
Clear skies, everyone.